I welcome you to the second practical session. Hope you've enjoyed your lunch. This time I have a slightly different set of assistants. So again, I'm here. And Artem is there to help you, just like in the previous session. And this time, instead of Ira, we have Maxim. A couple of minutes before the seminar, Maxim told me that the seminar is too simple. So apparently, Maxim is very smart, and he's there to help you. OK. So does the network work? No. Did you download everything in advance? OK, the pictures are not available, but I'll show them. During this session, we're going to discuss variational autoencoder for semi-supervised learning, which is, from my opinion, a very cool application of variational autoencoders for semi-supervised learning. And this is just another illustration that the whole framework is extremely flexible, and you can change it and tweak however you want, unlike, for example, plain autoencoders. And also, this model is a very nice illustration for which cases you really need discrete variables, because one of the hidden layers variables here is discrete. Let's discuss the notebook, and then you'll switch to the task. So it's almost the second part of the day. You're probably already very tired. So this time you'll have only one task. You'll have to implement one loss function. But it's quite complex, from my opinion. So here we download MNIST, but there are a few extra lines of code, because for our applications, I manually delete 95% of labels just to do semi-supervised learning. I do it like this. I load the MNIST dataset and then create a matrix to store labels. For the labels that we observe, I store one-hot encodings. And for the labels that we do not observe, I only store a vector of zeros. So to obtain a mask for the present labels, you can just sum across the categories, and you'll obtain a vector of length 60,000 that contains ones and zeros. Once if the variable if the variable is observed, and 0 in the other case. OK, that's it. So again, we'll use distributions from PyTorch distribution package module, but besides using Bernoulli and normal distributions, we'll also use so-called relaxed one-hot categorical distribution. This is the class that implements all the stuff that Artem was talking about, Gumbel softmax trick, specifically Gumbel softmax trick. So let's first ignore the model and look at the illustration. So here we have a small piece of code which is already complete that illustrates the work of Gumbel softmax trick. So this cell just generates some probability distribution and then samples from the Gumbel softmax. So those are distributions obtained with different temperatures. And those are samples from Gumbel softmax. Note that as the temperature decreases, it almost looks like one hot, which is what we want. So you can use this. And now let's switch to the model. So instead of having just one latent variable z, which encodes all of the information about the picture, now we'll have two distinct latent variables. One of them is z, and again, it will be a real vector that encodes some information about the picture. And besides that, we'll have a latent variable y, which is a latent variable, categorical latent variable that represents something. And so y is a discrete latent variable. We do not really control it by elbow, but we'll hope that after training, the model will use this latent variable to encode the digit class from NIST. So now let's turn to the pictures, which you cannot download. Not to the solutions. Okay, I'll have to update collaborator probably. Gorgeous, enormous pictures. So for this model, there are two possible cases. So one case is when we have label for our observation, and the other case when there is no label available. So whenever label is available, this thing works pretty much like plain variational autoencoder. It computes encoder with input x and the label that we have, then does the reprioritization trick, pushes the sample to decoder, and defines a conditional distribution. But note that now the conditional distribution is also conditioned on y, and we put y inside both encoder and decoder. So effectively, we condition the whole network on label y. So the network knows about the value of the variable when it computes anything. Okay, and the other case is when we do not have any variable y available. And for this case, we have to define an extra network. So the part of this picture looks like before. We have encoder. We put x and y into encoder, do a representation trick, put everything inside of decoder, define conditional distribution, that's it. But now we don't have y, so instead of plugging in the available value, we have to sample it. So we put x into specific new network y encoder, compute some logits, define Gumbel distribution, sample from it, and then put the sample both into decoder, encoder, and then everything works just before. So this is the assignment from the deep learning viewpoint. Okay, let's zoom into the formulas. For each of those cases, you have to compute specific loss function. So recall that the loss function that we use in variational autoencoders is just negative elbow, right? So there are two cases. When the variable is observed, so we want to compute likelihood for the observation to maximize likelihood. Likelihood is not available. We compute evidence lower bound because its approximation of the lower bound is computationally tractable. So the trick is just the same. You replace expectation with another expectation, apply Jensen inequality, and obtain this lower bound. This is almost the same as the lower bound of the vanilla VA. It's pretty simple. And the difference comes whenever y is unavailable. So in this case, you have to compute both expectations with respect to y and p of z given y. And this is the thing Artem was talking about, how to compute expectation with respect to discrete variable. So for MNIST, it's quite simple because you have only 10 classes and you can compute this expression for each of the possible 10 classes, sum them all, and forget about any problems. There are the number of classes is not exponential here, but note the following. Whenever we pick another y, we have to compute the network that decodes z and y, for example, once again. So if we have 10 classes, we'll have to compute everything 10 times. We have to compute decoder 10 times for each possible value. And imagine working on ImageNet instead of NIST. So the slowdown will be 1,000-fold instead of 10-fold. So in this case, sampling y with some stochastic procedure is really helpful from the computational viewpoint. So the idea here is to sample y from Gumbel distribution and to use the sample from Gumbel distribution in both of the networks. And it works. So the final detail I have to tell you about is that besides the two elbow terms in the loss function, there is a small hack in the whole framework, the semi-supervised VAE. So we want to use distribution Q of y given x for classification. Because look, it takes x as input and returns a distribution over classes, right? So this is the thing which we can use a classifier, right? And well, it turns out that if you just optimize those two elbows, the classification is not that good. And the authors propose to add a penalty term for the variational distribution Q of y given x. So the penalty term is just cross entropy computed for the observed variables. And this small penalty term really improves the performance of the model. So this is all that you have to know about SSV. You can read the paper it's proposed. So there is a link to the paper. Also, the whole model is described in detail in the notebook. And the task here is to implement the loss function to train this model. I have a small comment on the implementation. So recall that I did some hacks to define y's. So one hot vectors, some of which are just zero vectors, yes? So you can sum one of the core x's in this matrix to obtain a mask of zeros and ones. But some of you try to use this mask for indexing, which only works if the vector is Boolean. But you can also just multiply everything by this vector, and the components that are multiplied by 0 will be crossed out of the sum, and the components that are multiplied by 1 will still be there. So do not try the things that only work for Booleans. You can just multiply vectors. So the visualizations are like before. So you plot some samples, but now we plot samples with class fixed. So in our scheme, this means that we fix a specific value for y variable and then plug in different z's. So this is how it works. Here it is. So I fixed different values of y and sample z. And you can notice that style of the digits changes, although most of the digits are correct. So this 7 looks like 3 a little, although it also looks like 7. This is 8, which is very similar to 1. So this works. And if you'll take bigger networks, train it for more epochs, it will work better. A nice thing about this model is that you can implement a toy-style transfer model with this. You can fix z inferred by q of x given z and y, and then plug different y's with given z, and this will give you different, same style for different digits. Here it is. So here I encode one digit, compute a latent representation z of this digit, and then decode it with different y's. So this digit is thin and curvy, and the style captures this, although some of the digits are incorrect. Those are three ones, but the digits are different. So, and personally, I think that the model captures the style. And the nicest thing about this model, from my opinion, is that you can also plot latent representations, and they are highly interpretable. So again, here we plot t-SNE for z's, which were very informative of the digit class for vanilla operation autoencoder, which you've implemented during the first session. And now the t-SNE plots are not so informative. The classes are mixed. There are some clusters of ones, but in general, the digits are mixed, and that does not learn much information about the variable class. But at the same time, latent representations of outputs of q of y given x, y encoder, y encoder, they are extremely informative of the class. So the cluster, there are some tiny errors, although they form distinct clusters. They do not fall into one circle because we don't have any Gaussian prior of them. And they form disconnected regions in the representation space. So this model, to sum it up, successfully decomposes information into one variable and another, information about class and the style. Now let's switch to the implementation. We have almost no time. Give me just 2 minutes. So my implementation completely follows the description of the function. I define one Gumbel distribution with encoder output as logits. I sample from this. I then compute the input to decoder network, which is sum of Gumbel samples masked by this variable and the observed variables, also masked. Then I sample from normal distribution for Z, which takes X and Y as input. This network takes X as Y as input, then defines mean and scale, and defines normal distribution. Again, one more sample. Then I define all the distribution that are named with the letter P. Distribution P of Y, distribution P of Z, which is standard normal, and distribution P of X given Y and Z, which is again Bernoulli. Now I've defined everything I need, and then I just sum the losses, some different terms to compute the loss. So this part is for P part of the loss, P of X given Y and Z, P of Z. Then I subtract Q of Z given X, Y. So this part is there both for observed and unobserved. And then for the observed variables, the unobserved variables, I add this summand, which is prior distribution minus posterior distribution of Y given X. And I forgot to include P of Y for the observed variables, but it does not change anything. And also the auxiliary penalty, here it is, just scalar product of vectors. I sum it all, and the loss function is complete. Feel free to check this at the GitHub. I'll fix the missing P of y, but again, it does not change anything. Thank you. Yes? All the latent are unobserved. All of the labels are unobserved. So what do you mean by work? It will work as plain variational autoencoder. It will reconstruct the images somehow. But I think that WISE will be really uninformative. So from the experience, even without this penalty, even with Y observed, the model does not work so well. So I think it will not work for classification.